A weapon sitting on the front of a single American destroyer right now that wasn't supposed to be ready for real combat yet. According to nearly everyone who had followed this specific program's slow, quiet progress through the defense procurement pipeline over the preceding several years, it spent 8 years in development. Its most recent successful test happened just weeks before this war even started, a timing detail that turned out to matter enormously. And then, almost by accident of timing, it ended up becoming the first weapon of its kind in the history of naval warfare to actually shoot something down in a live, ongoing war. That weapon just broke the entire economic logic behind how Iran has been trying to fight in the Strait of Hormuz, a logic Tehran had spent years building and refining. And almost nobody outside of a handful of defense outlets actually explained why that matters. So let's fix that today. Think about what it actually means for a program to spend 8 years in development and only reach a successful test weeks before the exact war it would end up needed for. That's not a coincidence that gets discussed much, but it should be. Most advanced weapon systems either arrive years too late for the conflict that could have used them, or they get rushed into service half-finished under wartime pressure and fail when it matters most. This is neither of those stories. This is a program that happened to cross the finish line at almost the exact moment a war broke out in the exact region it was built to operate in, off the coast of a country whose entire drone strategy it was uniquely positioned to dismantle. Whether Tehran's own military planners ever anticipated a weapon like this reaching maturity this fast is a fair question, and based on how their drone campaign has continued largely unchanged since, the answer looks like no, at least not yet, though that could shift quickly once the full implications of this engagement work their way through Iranian military planning circles. Here's what's coming. We're going to break down exactly why Iran's strategy in the Strait was built around a simple math problem that was working in Tehran's favor. We're going to introduce the actual weapon, what it is, who built it, and how long it sat in development before anyone expected it to see real combat. We're going to walk through exactly how it works, including the parts that don't work as well as the headlines suggest. And we're going to connect it to the broader campaign to reopen the Strait of Hormuz, including an assassination that most people missed entirely. So stick with me, because this story starts with a spreadsheet, not a battlefield. Let's start with the math, because the math is the entire reason this specific story actually matters as much as it does. When the current conflict, now formally tracked as the 2026 Iran War, began on February 28th with joint American and Israeli strikes, Iran responded by launching its own bombardment campaign against the countries, hosting American forces across the region. And the weapon of choice for that campaign wasn't Iran's most sophisticated hardware. It was something much cheaper. The Shahed 136, a Tehran-designed and built attack drone, costing somewhere between $20,000 and $50,000 per unit, according to reporting from Euronews on the economics of this exact standoff. Now compare that to what the United States has been using to shoot those drones down. Patriot interceptor missiles, running $3 to $4 million each. THAAD interceptors, which run about $10 million per shot. Sit with that gap for a second. A $50,000 drone, in the worst case for Iran, forcing the United States to spend up to $10 million to knock it out of the sky. That's not a fair fight in the way people usually mean that phrase. That's a deliberately engineered cost imbalance, and it's a tactic that shows up again and again in modern asymmetric warfare, because even a country with a fraction of America's military budget can bleed a superpower financially if the exchange rate on every single engagement favors the cheaper side by that many multiples. This isn't a new insight in military strategy circles either. Cheap, disposable weapons, designed specifically to provoke an expensive, disproportionate response, have been a core feature of asymmetric conflict for decades. From improvised roadside devices costing a few $100s, forcing multi-million-dollar vehicle replacements, to small drones costing a few $1,000s, forcing operators to expend interceptor missiles that cost 1,000 times more. What makes Iran's application of that same logic in the Strait of Hormuz notable is the sheer scale of the mismatch and the sheer volume of drones Tehran has been able to manufacture and launch. The Shahed 136 program didn't appear overnight. Iran has spent years refining both the design and the manufacturing pipeline behind it, building toward exactly this kind of sustained, high-volume, low-cost campaign, one specifically engineered to be economically unsustainable for whoever has to keep shooting each individual drone down. A strategy that has worked reasonably well against multiple adversaries in multiple theaters over the past several years, long before this specific war ever began. And the American military budget dwarfing Iran's didn't actually solve this problem, because raw budget size doesn't matter if the per-engagement economics are backwards. The United States spends roughly $900 billion a year on defense. Iran's entire defense budget for 2025 sat around $23 billion, a gap of nearly 40 to 1 on paper. But budget totals don't win individual engagements. Individual engagements get won or lost based on what each side pays per shot. And by that measure, every single successful Patriot or THAAD intercept against a Shahed 136 was a loss disguised as a win. According to a Trump administration official cited by Euronews, the war had already cost the United States $12 billion in its first 3 weeks alone, working out to just under $1 billion a day. A meaningful chunk of that bill traces directly back to this exact math problem: expensive interceptors being burned through against cheap, disposable drones, week after week, strike after strike, month after month. Think about $1 billion a day actually means over the full span of a war that, by this point, has been running for months rather than weeks, a duration nobody predicted when the first strikes landed back in late February. Even if that early burn rate slowed down as the conflict matured, the cumulative bill for defending against a drone campaign built on $50,000 hardware, using $3 to $4 million interceptors, adds up into the tens of billions of dollars territory extremely quickly. And that's before accounting for the cost of replacing depleted interceptor stockpiles that can take manufacturers years to rebuild at full production capacity. That's real money, appropriated by Congress, drawn down from actual stockpiles that take years to replenish, all being spent to intercept weapons that Iran can manufacture in a fraction of that time for a fraction of that cost. No military, regardless of its overall size, can sustain that kind of exchange rate indefinitely without either running through its interceptor stockpiles or fundamentally changing the economics of the fight. So Washington needed something that could break that equation, not by building a cheaper missile, but by building something that didn't need a missile at all. And that's where Helios comes in. Helios stands for High Energy Laser with Integrated Optical Dazzler and Surveillance, a name that sounds almost too elaborate for what is, at its core, a remarkably elegant solution to a very expensive problem. It's a 60 kilowatt high-energy laser weapon built by Lockheed Martin, designed specifically to intercept drones, aircraft, and missiles. According to Euronews' technical breakdown of the system, Lockheed Martin won the contract to develop this weapon all the way back in January of 2018. Sit with that timeline. 8 years of development, testing, refinement, and integration work, all leading up to a successful test in February of 2026, just weeks before this war actually began. This wasn't a weapon rushed into existence in response to the conflict. It was a program that had been grinding through development for the better part of a decade, and it happened to reach operational maturity at almost the exact moment it was needed most. 8 years is a long development timeline even by the standards of the defense industry, and it's worth understanding why a laser weapon takes that long to mature when a conventional missile system can sometimes reach production in a fraction of that time, particularly when the underlying missile technology already exists in some prior form and simply needs adaptation. Directed energy weapons like Helios aren't just about generating a powerful enough beam. They require solving an entire cluster of separate engineering problems simultaneously. You need enough continuous electrical power generation on board a ship to sustain repeated firing without draining systems needed for propulsion or other weapons. You need precision optics and tracking systems accurate enough to hold a beam on a small, fast-moving target across kilometers of open air, compensating in real time for the ship's own movement on open water. A targeting challenge that gets significantly harder the smaller and faster the incoming threat happens to be. You need thermal management systems to prevent the weapon itself from overheating during sustained use. And you need all of that integrated into a single system reliable enough to actually deploy on an active warship in a combat zone, not just something that works in a controlled test environment. Lockheed Martin, spending the better part of a decade solving that entire cluster of problems simultaneously, is exactly why this program looked, for years, like exactly the kind of ambitious defense project that quietly slips year after year without ever reaching the fleet. As of the most recent reporting, the USS Pribble, an Arleigh Burke-class destroyer, is the only ship in the entire United States Navy actually equipped with Helios, and it's currently deployed off the coast of Iran. One ship, one laser. That's the entire operational footprint of this system right now, which makes what it's already accomplished even more remarkable. Last week, according to Euronews reporting, the USS Preble used Helios to down several Iranian drones in actual combat. Multiple outlets independently confirmed the engagement, including the New York Post, Gulf News, LiveMint, and GB News, all reporting that Helios had engaged Iranian drones during the current campaign. Defense analysis from Next Big Future placed this in its proper historical context. This is the first known combat deployment of a high-energy shipboard laser in this entire conflict, and one of the first confirmed combat uses of a directed energy weapon of this kind anywhere in naval history. Before the war even started, that same reporting noted the USS Preble had already downed 4 drones in expanded testing back in early February, which tells you the Navy was already building operational confidence in the system in the weeks immediately before it needed to use it for real. That detail about the pre-war testing is worth sitting with for a moment, because it shows This wasn't a weapon that got thrown into a war zone the moment the shooting started. The Navy had already been quietly running expanded tests on the USS Preble specifically, in the exact weeks leading up to the February 28th outbreak of hostilities, downing drones under controlled conditions before ever needing to do it under fire. That kind of pre-war operational testing, happening on the exact platform that would go on to make history days or weeks later, is either an extraordinary coincidence of timing or a sign that Navy planners already had a strong sense of where this conflict was heading and made a deliberate decision to have their most advanced counter-drone system combat-ready and forward deployed before the first shot was fired. Here's how it actually works, because the mechanics matter for understanding why this breaks Iran's cost equation so completely. Helios can strike a target two different ways. At low energy intensity, it can dazzle a target, meaning it confuses the target's guidance system badly enough to force a crash without necessarily destroying the airframe outright. At high energy intensity, it can kill the target directly, overheating it until it fails structurally. Lockheed Martin describes the system as more than just a laser, calling it a fully integrated weapon system. And that integration matters, because Helios isn't just an offensive tool. Thanks to built-in thermal imaging, night vision, and ultra-high-definition optics, it can also identify, track, and assess targets from as far away as 8 kilometers, functioning as a surveillance and reconnaissance system even when it isn't firing. And according to Lockheed Martin, the current architecture is already scalable well beyond its current output, with the potential to reach 120 kilowatts as the technology matures further. The dazzle versus kill distinction is worth understanding a little more deeply, because it gives the operators on board the USS Preble a level of flexibility that a traditional missile interceptor simply doesn't offer. And that flexibility itself has real tactical value beyond the raw cost savings. A Patriot or a THAAD interceptor has essentially one mode: launch, track, and destroy through kinetic impact or proximity-fused warhead. There's no lower intensity option, no way to disable a target without fully expending the interceptor. Helios, by contrast, lets an operator choose exactly how much energy to commit to a given target based on the threat level. A cheap, unsophisticated drone that just needs to be knocked off course might only require the lower intensity dazzle setting, saving power and time for a follow-on target that requires the more energy-intensive kill setting, essentially letting a single operator ration the weapon's output across an unpredictable evolving threat picture in real time, rather than committing fully to every single target, regardless of how serious the actual threat turns out to be. That flexibility matters enormously in a scenario involving drone swarms, where a ship might be facing multiple incoming threats simultaneously and needs to triage its response across several targets in a matter of seconds, prioritizing the most dangerous incoming threats while conserving energy against the least sophisticated ones. The scalability point deserves attention too. 60 kilowatts is the current operational output on the USS Preble, but Lockheed Martin's own claims put the architecture's ceiling at double that, 120 kilowatts, without requiring a fundamentally different system design from what's already been engineered, tested, and proven at the current output level. That matters because laser weapon effectiveness generally scales with power output, meaning a future upgrade path exists that could extend Helios's effective range, its ability to punch through adverse weather conditions, and its speed at neutralizing a given target, all without needing to design and field an entirely new weapon system from scratch, which is a meaningfully faster and cheaper path to a more capable system than starting over from a blank sheet of paper. Whether that upgrade path gets pursued quickly, given how urgently useful even the current 60 kilowatt version has already proven to be in real combat, is exactly the kind of decision that tends to accelerate fast once a weapon starts demonstrating this kind of value under fire, especially when the alternative is continuing to burn through multi-million-dollar interceptors at the current unsustainable rate. Now here's the number that actually matters more than any of the technical specifications. Every time Helios fires, the cost is measured in electricity, not munitions. Euronew's own framing put it bluntly, describing the technology as capable of bringing the cost of shooting down a drone from several $1 million down to just a few cents. Read that against the numbers we just walked through. A $50,000 Shahed 136 drone, previously forcing a $3 to $4 million Patriot interceptor or a $10 million THAAD interceptor to respond, now facing a weapon that costs next to nothing to fire, again and again and again, for as long as the ship generating its power stays in the fight. That's not an incremental improvement to the cost equation. That's a complete inversion of it. The weapon that was supposed to be too expensive to sustain a prolonged drone war is suddenly the cheap option. And the $50,000 drone that was supposed to be the cost-effective weapon is now the expensive one, because it gets destroyed for pennies instead of forcing a multi-million-dollar response. Think about what that inversion means in practical terms for a ship's magazine capacity too, not just its budget. A destroyer can only carry a finite number of Patriot or Standard missile interceptors before it needs to return to port and rearm, which means a sustained enough drone swarm could theoretically exhaust a ship's interceptor stockpile even if the ship survives every individual engagement. A laser weapon doesn't have that same magazine limitation in the same way, since its only real constraint is the ship's continuous power generation capacity, rather than a fixed number of physical rounds loaded before departure. That means Helios doesn't just save money per engagement, it also extends how long a single ship can keep fighting off a sustained drone campaign before needing to break contact and resupply, which is its own separate, meaningful tactical advantage layered on top of the cost savings. But I want to be honest with you about where this technology still falls short, because a story like this deserves the full picture, not just the highlight reel. Helios has real documented weaknesses. According to Euronews Technical Breakdown, its effectiveness is limited by rain, smoke, dust, clouds, fog, and other atmospheric interference, all of which scatter the laser beam and degrade its ability to hit a target cleanly. The weapon also requires a significant amount of continuous electrical energy to fire, which means it's tied directly to the power generation capacity of whatever ship is carrying it, and it has a limited effective range, compared to a missile that can travel for miles before impact. None of that erases what the system already accomplished in real combat, but it does mean Helios isn't some flawless silver bullet that instantly solves every problem in this drone war. It's a powerful new tool with real, specific limitations that any adversary paying attention would immediately start trying to exploit, whether that means timing attacks for bad weather, saturating the system faster than it can track and engage each individual target, or simply overwhelming a single ship's power generation with a large enough simultaneous swarm. Think through what each of those specific weaknesses actually means operationally, because they're not abstract technical footnotes, they're exploitable gaps. The Strait of Hormuz isn't a controlled laboratory environment. It's a body of water that regularly experiences haze, dust storms blowing in off the Arabian Peninsula, and periods of reduced visibility, any one of which could meaningfully degrade a laser weapon's effectiveness at exactly the moment an adversary might choose to launch an attack. If Iranian planners are paying close attention to what happened aboard the USS Prebble, and there's every reason to assume they are, the obvious tactical adjustment is to start timing drone launches for exactly the weather conditions that scatter a laser beam most effectively, essentially trying to route around the new capability rather than confronting it head-on. That's how asymmetric warfare typically evolves. One side introduces a capability, the other side adapts its tactics to minimize that capability's effectiveness, and the cycle continues. The power generation constraint is worth unpacking a little further too. A destroyer's electrical systems have to balance multiple demands simultaneously: propulsion, radar, communications, other weapon systems, and now a laser that draws heavily on that same shared power budget every time it fires. That means there's likely a practical limit to how many consecutive engagements Helios can sustain before the ship has to manage power allocation carefully, especially if it's simultaneously trying to maneuver at speed or run other high-draw systems at the same time. A sufficiently large, coordinated drone swarm, timed to arrive faster than the laser can track, engage, and reset for the next target, could theoretically still overwhelm a single ship defense, even with a weapon this capable mounted on the bow. And that single ship limitation is worth sitting with for a moment, because it's the most important caveat in this entire story. Helios being combat-proven doesn't mean the Navy suddenly has a fleet-wide answer to the drone problem. It means the Navy has one proof of concept, deployed on one destroyer, in one specific theater, that has now demonstrated it can work exactly the way its designers hoped it would after 8 years of development. Turning that single successful deployment into a fleet-wide capability that could actually neutralize Iran's broader drone strategy across the entire Gulf would require years of additional shipbuilding, integration, and production, none of which happens on the timeline of a single ongoing war. So, while Helios broke the cost equation in this one specific engagement, on this one specific ship, it hasn't yet broken Iran's overall strategy across the entire theater, and that distinction matters enormously for anyone trying to understand where this technology actually stands right now versus where the headlines might make it sound like it stands. Now let's connect this to the bigger picture, because Helios isn't operating in isolation. It's part of a much larger campaign specifically focused on reopening the Strait of Hormuz, and understanding that campaign explains exactly why a laser on a single destroyer matters as much as it does. According to the Wikipedia tracker for what's now formally documented as the 2026 Strait of Hormuz campaign, the United States began a dedicated aerial campaign against Iranian targets on March 19, 2026, specifically aimed at reopening the strait to international shipping after Iran closed it in response to the opening strikes of the broader war. The stated goal was straightforward: destroying the Iranian naval vessels and drones that had been targeting shipping in the strait. And in the middle of that campaign, Israel carried out a targeted operation that barely made headlines outside specialist defense coverage. According to that same tracker, Israel assassinated Alireza Tangsiri, the naval officer overseeing Iran's blockade of the Strait of Hormuz, taking out the specific commander responsible for coordinating that blockade in the middle of an air campaign built around a laser weapon capable of shooting down the cheap drones that blockade depended on, tells you this wasn't a series of disconnected, isolated actions. It was a coordinated effort to dismantle both the human leadership and the technical strategy behind Iran's entire approach to controlling that waterway, happening on parallel tracks at the same time. Losing the specific officer who had been overseeing that blockade is a different kind of blow than losing hardware. Naval blockade operations, especially ones built around coordinating swarms of small, cheap, dispersed assets like drone boats and mines across a narrow strait, depend heavily on centralized command and control to synchronize timing, targeting, and resource allocation across multiple simultaneous threats. Removing the officer who had built and was running that coordination effort doesn't just cost Iran a single individual. It potentially disrupts the institutional knowledge and operational rhythm that blockade had been running on, right at the exact moment the technical side of that same blockade strategy was starting to face a genuinely new countermeasure in the form of a combat-proven laser weapon. Whoever inherited responsibility for the blockade after Tangsiri's death had to simultaneously rebuild that command structure and adapt to a threat environment that had just fundamentally shifted, a very difficult position to be in during an active, ongoing war. The campaign kept escalating from there. On April 13th, 2026, following the collapse of ceasefire talks in Islamabad, the United States imposed a full naval blockade of Iran. In early May, a specific operation called Project Freedom ran for a few days before a temporary halt. And through all of that escalation, the underlying problem never actually went away. Iran kept launching cheap drones and small boats into the strait. And the United States kept needing something that could shoot them down without bankrupting itself one interceptor at a time. That's the exact gap Helios was built to fill, and that's exactly why its first confirmed combat kills matter so much more than a single tactical engagement normally would. Because here's the strategic reality underneath all of this. Iran's entire approach to contesting the Strait of Hormuz was never built around matching the United States ship for ship or missile for missile. It couldn't, and Iranian planners have known that for years. Instead, the strategy was built around exactly the kind of cost asymmetry we walked through earlier, cheap drones and small boats designed specifically to make every single American response disproportionately expensive, betting that the financial pressure of that imbalance would eventually force Washington to either back off or bleed itself dry trying to keep the strait open. A weapon that can intercept those same cheap drones for a few cents in engagement doesn't just win one battle. It attacks the entire foundation the strategy was built on. If the cost of defending against a Shahed 136 drops from millions of dollars to essentially nothing, the entire logic behind flooding the strait with cheap drones in the first place starts to fall apart, at least on any ship carrying a weapon like this one. That's also exactly why this story deserves more attention than it's gotten. A single successful missile intercept is a tactical event that happens and gets forgotten within days. A weapon that inverts the fundamental cost structure of an entire theater of war is a strategic event, one that can reshape how both sides plan their next moves for months afterward, regardless of how many ships actually carry that weapon on any given day. Iran's own commanders now have to factor in the possibility that any given American destroyer might be carrying a system that makes their cheapest, most numerous weapon essentially worthless in that specific engagement, which changes the calculus of every single drone launch, even the ones aimed at ships that don't actually have Helios installed. Uncertainty itself becomes a deterrent once the capability has been proven even once in real combat. There's a broader lesson here too, one that extends well past this specific war. For years, defense analysts have debated whether directed energy weapons would ever move past the demonstration stage and actually prove themselves in a real, sustained combat environment, rather than remaining a promising but unproven technology perpetually 5 years away from operational relevance. The USS Preblay's engagement against Iranian drones in the Strait of Hormuz answers that question, at least partially, in the affirmative. It happened. It worked. It was independently confirmed across multiple outlets. Whatever comes next for this specific war, that milestone itself now belongs to the historical record of naval warfare. The moment a directed energy weapon moved from research literature and defense trade publications into an actual documented combat kill against a real adversary's weapon system. So, here's where this leaves us. A weapon that spent 8 years quietly working its way through development, that had its last successful test just weeks before this war even started, ended up becoming the first shipboard high-energy laser in history to score a confirmed combat kill. And in doing so, it inverted the exact cost equation Iran had been counting on to sustain its entire drone campaign in the Strait of Hormuz. That's not hype. That's the actual arithmetic, verified across multiple outlets, laid out side by side. $50,000 drones, multi-million-dollar interceptors. And now, a weapon that costs pennies to fire, still limited to a single ship, still vulnerable to bad weather and power constraints, but already proven in combat exactly the way its designers spent 8 years hoping it eventually would be. What happens next depends on how fast the Navy can turn one proven system on one destroyer into something closer to a fleet-wide capability, and on whether Iran adapts its drone tactics fast enough to work around a weapon that's already shown it can shoot Shaheeds down for the cost of the electricity it takes to fire. Do you think this technology scales fast enough to matter for the rest of this war? Or does it stay